We're going to move on now to conductors, meaning conduits in which charge can flow. So we're going to move charge from one point to another, and how well the charge flows depends on how much of a conductor a material is. So a conductor is defined as a material in which charge flows freely. Often we're talking about metals. An insulator is a material that has almost no charge flowing through it at all. So you have other materials. So for example, down here, you have two particles, one positively charged, one neutral, and you connect them with a metal. Some of that charge is going to flow through the metal and then evenly distribute itself across the two objects. The metal is then a conductor because it allows the charge to flow freely. But if you do the same thing with wood, then it's going to block the charge. The charge will not flow, and so wood is a good example of an insulator. Now there are some materials that are called semiconductors, and by a semiconductor we mean charge flows, but not as easily, readily, or quickly as it does through a metal. Now, you can actually charge a neutral rod through conduction, the motion of charges. So here in example A, if you have a neutral rod, so here's your neutral metal rod, no charge, well, all charges are balanced. There's no imbalance of electric charge. And then you bring a positively charged rod. Well, positive charges are attracted to negative charges, which means electrons are going to flow from this neutral metal rod into your positively charged rod A. And once you bring that charge, the rod A, away, you're taking the electrons away with it. What's left is a positively charged rod B. You can also charge something through what we call induction. So we have here a neutral rod in A that is what we call grounded. We're going to define grounding more in a future chapter, but basically a ground is this is the symbol for a ground. A ground is a path that it's a common conductor that allows negative charges to flow through. Okay? So you have this neutrally charged rod that is grounded. You bring a negatively charged rod close. The negative charges pull all the positive charges toward it and push all the negative charges away from it. Since it's grounded, the ground means a common conductor that allows the negative charges to flow out of this rod. These didn't even touch. They never touched. So when you move the negatively charged rod away, all the negative charges are gone. They went through the ground, and you're left with a positively charged rod. That's what we mean by induction, charging an object by induction. Non-conductors won't become charged by conduction or by induction. However, they may experience a separation of charge. For example, let's say that this is a block of wood. You have a block of wood here. You bring a positive charge to it, you're not going to have any positively or negatively charged wood. It's not going to happen. However, you can experience a slight separation of charge. So it can take a region, and the negative charges in that region will move towards the positively charged rod, and the positively charged portions of that region are pushed away. Here's a cool device that uses these principles of conduction and induction to detect the charge in a material. Here's how it's made. You have a metal ring, and it's hollow. Sometimes you have a glass cover on it, sometimes you don't. The electroscopes I have in my lab do not have glass covers on them, but they work just fine. It's not an issue. And then you have a metal ball up here that's insulated from the metal ring around it. And that metal ball, however, is connected to two leaves of gold underneath. Doesn't have to be gold. There are different ways to do it, but we'll use the gold one in this case. And here's what happens. If you bring a positively charged rod, then all the negative charges flow up, and all the positive charges are repelled, so they're pushed down. And that is going to charge my gold leaves positively, and since like charges repel, these gold leaves are going to move away from each other and are going to they're going to repel each other, so the gold leaves will spread out, showing that there is an electric charge in the rod. Okay. But in figure B, we're moving from, figure A is induction. We have induced an electric charge. If we pull the positively charged rod away, then all the new charges will recombine, and the gold foil will return back to normal after the rod disappears. However, if you actually touch the rod to the metal, then you get conduction. You get negative charges which flow up and then into the metal rod, so that when the rod leaves, then you are left with a positive charge everywhere. So by conduction, you keep the separation of the gold foils because of the charge inside of your electroscope. If you do that, here's another example of one where you brought a negatively charged rod in. So you brought in a negatively charged rod, and so all the positive charges have left, leaving the rod negatively charged through conduction. Okay, I'm going to get rid of that. So we have an electroscope that is negatively charged. If you bring a negatively charged rod close to the electroscope, that's going to push all the negative charges away, which is going to increase the negative charge of your gold foil, causes them to spread out. But if you bring a positively charged rod, then all the electrons that were down here move up to the top, leaving the gold foil less negatively charged. Since it's less negatively charged, the gold foils are going to pull back towards each other. They're going to repel each other less. So there's a few good experiments and ideas, not only in conduction, but also induction and measuring charge through electroscopes.